The development of China's new high-speed compound helicopter marks a continuation of its broader strategy to close technological gaps in aerospace and assert itself as a peer competitor in advanced military aviation. While details about the helicopter's exact specifications remain limited, its configuration signals an intent to break away from traditional helicopter designs in favor of platforms that offer greater speed, agility, and mission flexibility. The coaxial rotor and pusher propeller setup is an uncommon but increasingly relevant architecture, long pursued in the United States and Russia, and now entering China's development efforts. Coaxial rotor systems are complex but advantageous. By stacking two rotors rotating in opposite directions on a single axis, the torque that a helicopter usually has to cancel with a tail rotor is inherently balanced. This allows all engine power to be used for lift and thrust. The design also improves stability and maneuverability, particularly in hover and low-speed flight. When combined with a pusher propeller at the rear, the aircraft gains significant forward propulsion without requiring tilting the main rotor disc, enabling higher forward speeds. This is the defining trait of a compound helicopter, an attempt to merge the vertical takeoff and landing capability of a traditional helicopter with the forward speed characteristics of a fixed-wing aircraft. China's pursuit of this type of rotorcraft demonstrates several strategic motives. First, it reflects a desire to modernize its helicopter fleet with platforms that can support rapid response missions in a range of environments, including mountainous terrain, urban areas, and contested zones near coastlines or island chains. Traditional helicopters are limited by top speeds of around 250 to 300 km per hour, making them vulnerable in fast-paced modern combat scenarios, especially against adversaries with advanced air defenses and long-range precision fires. A high-speed rotorcraft with improved survivability and performance could serve critical roles in troop insertion, casualty evacuation, and reconnaissance, while also supporting special operations and potentially unmanned teaming in the future. Second, the decision to showcase such a prototype indicates an ambition to compete with, or at least mirror, the development trajectories of other major military aviation programs. In the U.S., the Future Vertical Lift (FVL) initiative has produced designs like the Sikorsky S-97 Raider and the SB-1 Defiant, both of which use similar compound rotor concepts. These platforms aim to exceed 400 km per hour in forward flight, with agile maneuvering and reduced acoustic signatures. China's version appears to align with these principles in theory, even if the technical execution is still unverified. The resemblance could be interpreted as an attempt to suggest technological parity or catch-up, particularly in the eyes of international observers. However, matching the external shape or propulsion layout of advanced rotorcraft is only one part of the equation. True capability lies in integration, how well the systems, materials, controls, and mission payloads work together. Developing a working prototype is a significant step, but transitioning that prototype into a reliable, mass-producible, field-ready platform is a far greater challenge. It involves not only refining the aircraft's aerodynamics and flight envelope but also maturing subsystems such as engine cooling, rotor vibration dampening, electronic warfare suites, communications, and flight control algorithms. Achieving this level of integration and reliability requires years of testing and iteration, usually under varying environmental and operational conditions. Another key factor is engine technology. High-speed rotorcraft demand high power-to-weight ratios, especially during transitions between hover and forward flight. Historically, China has faced challenges in producing high-performance, compact turbine engines for helicopters, often relying on imported engines or reverse-engineered models with lower thrust and shorter service lives. If the new compound helicopter is to meet its design potential, it must be powered by an engine that can sustain high speeds and temperatures over extended periods without failure, a non-trivial demand in vertical lift aircraft. The aerodynamic loads on coaxial rotors are another technical hurdle. These systems experience high stresses during maneuvering, especially at high speeds, and managing those loads requires composite materials and precision manufacturing. Advanced avionics and flight control software are also necessary to stabilize the aircraft across a wide flight envelope, particularly during complex transitions from hover to cruise. The U.S. systems, for instance, incorporate fly-by-wire systems with advanced stability augmentation, areas where China is improving, but where consistent, combat-tested performance has not yet been demonstrated. In terms of development strategy, unveiling a prototype could serve several overlapping purposes. Domestically, it can reinforce narratives of technological advancement and military modernization. It signals to national leadership and internal audiences that investments in aviation R&D are producing visible outcomes. Internationally, it may function as a soft power projection tool, aiming to attract interest from foreign militaries or influence global perceptions of China's defense innovation capabilities. However, such signaling can also generate skepticism if performance claims remain unproven in real-world environments. It's important to note that not all advanced-looking prototypes translate into operational success. Over the past decades, several countries have introduced ambitious aircraft designs that either failed to reach production or were heavily revised due to technical limitations. The key challenge for China will not be just flying a prototype, but turning it into a platform that can be manufactured at scale, deployed reliably, maintained in the field, and adapted to evolving mission profiles. This involves establishing a full ecosystem of training, logistics, spare parts, and support infrastructure, all of which are crucial for military aviation readiness. Furthermore, operational success depends not just on the helicopter itself but how it fits into a larger command, control, and communications network. A fast helicopter is useful, but it must be integrated into a battle network with drones, ground forces, sensors, and targeting systems to fully realize its potential. This demands software-driven, interoperable systems that can share data in real time, resist electronic warfare, and enable coordinated operations. Building this ecosystem is a long-term effort that goes beyond any single airframe. China's compound helicopter program, regardless of whether it reaches full maturity soon, shows a clear intent to explore and potentially adopt technologies that allow for greater battlefield mobility, reduced response time, and survivability in modern combat environments. It reflects broader themes in global military aviation: speed, agility, autonomy readiness, and network integration. The true measure of success will not be the prototype's first flight, but its ability to perform consistently in complex, real-world operations under stress. Until then, the program remains a work in progress with strategic implications and uncertain operational outcomes.